Je suis Binois from Airbus Elancourt, and I will present you with my colleague Mirko from TESAT Backlong the experience on SEO testing we have in Airbus. First, the team, we are two here today. I will talk about the SEO test activity overview we have in Airbus and TESAT since many years. We'll try to present you also just an overview of a few test bench we developed for different tests. We have mainly a generic test board which can be reused very easily to test a new device and very quickly. And sometimes we have to develop also one-shot test bench for more complex devices. And Mirko will present you the RF test bench, which is also another topic. We'll talk also about the test problematic, mainly 3 points: setup design, the facilities, but I think most of you know what is a facility, and a focus on the device preparation, mainly about plastic devices. A test activity in Airbus, we can summarize around 600 tests in 2003. Our activity is mainly dedicated to provide SE behavior of devices we used for ADS project. This activity is fully integrated in the procurement process at early level. I mean that we try to have as much of possible information about the traceability of devices, so as in the future, for a new procurement, we can avoid a huge number of tests. We also have some internal R&D activities for ESAC, NES, and DLR, and also some external customer, but most of them are related to ADS projects. Now we'll have an overview of existing test bench, some existing test bench, because we have a lot. Generic test bench we use, I call generic because we use it very frequently. And the first one is multiple devices test board, MOSFET, high voltage diode, memories, and after I will talk about one-shot test bench, high frequency devices, optical sensor, and complex ASIC, and also RF test bench. So this is the so-called X-Multi test board. So we have 4 test slots. So as you don't have to open the chamber or to access the room. Mainly, everything is remotely controlled. We can develop in a few days a new test setup for a new device. In fact, it's only to develop this daughter board. And we are able to test latch up, SEU, SET, can be at the same time or separately depending on the device. And we can manage op-amp, comparators, voltage, ref, regulators, ADC, DAC, and all the most simple digital circuits. We also have a MOSFET test bench with 8 slots. You can see here. We can manage both N and P channels. The power can be up to 600 for the VDS and plus minus 100 volt for VGS. Don't worry, most of the MOSFET we test are limited up to 20, but This was for a study where we tried to go up to reach the limit, and sometimes we find MOSFET which are able to withstand up to 60, 70 volts. We have ACB detection and drain charge collection integrated. Drain charge collection is very useful because each time you have a particle which strikes the die, you have a pulse, and it's very easy to check if you are the beam which is focused at the device you plan to test. We can also measure the VGS threshold for N channel. P has to be added. The PIGS functionality is also available. All is remotely controlled. And we also have integrated an auto test which allows to test that the device is really connected. Otherwise, you may find it non-sensitive. In the same way, we also developed recently a high voltage diode test bench. We can go up to 1,000 volts, and design limit is 7 kilovolt, but there is a regulation which requires you have a special clearance to work above 1 kilovolt. We have a temperature monitoring with heating option if necessary, and the reverse current is monitored online between 10 picoamps to 20 milliamps. And also, we also have an auto test integrated to check if the device is well connected. Next is a flash memory tester. On this tester, the challenge was to have something running at maximum frequency. So we have 40 mega asynchronous mode and 20 mega asynchronous DDR mode. We have different adjustable supply and protected as well. Embedded processor and FPGA, which is very close to the device, so it can be managed at maximum speed. All is remotely controlled with only one internet connection, which is very easy when you go to facilities where you have a long distance between the irradiation stand and the control room. And also, we have integrated a high-speed hard drive for data recording, because this kind of device can offer up to 500 gigabits. And if you plan to test it and you have a huge amount of error, you can imagine the number of gigabytes of error you will produce during a test campaign. Now we'll switch to the Oneshot test bench. I selected this one because it's a very high frequency device. It's a 3 giga sample per second mux stack, and the output signal is a high frequency signal, and you have 4 different modes. The carrier here is around 3 giga, and the challenge was to be able to detect any transient which can arise on the output signal during irradiation. And here you have different examples of what we get during the test. But for that, we had to develop a dedicated analog trigger, because we didn't find any valuable solution on the existing oscilloscopes. The next is for an optical sensor. This is an infrared sensor, uncooled infrared. And the first goal of the test was to assess the SEL sensitivity, because this sensor was known to be SEL sensitive, but was selected to flight, and it was mainly for the delature design to protect. Additionally, we tried to get some information about the ACT on the video signal, and we had to work at 6.6 megapixels per second. And the solution to compensate for the fact that we cannot regulate the temperature around the sensor, so we can, it was difficult to have a stable signal, I mean a long-term stable signal. So we decided to perform an image-to-image comparison to detect ACT. And the result was around, the best case was 40 millivolts. I mean, when a pixel has a value different for more than 40 millivolts from the previous value on the previous image, it's considered as a ACT. And due to latch up, we also had an optical stimuli. So for infrared sensor, it's really easy. It's just you put in front something which you can hit, and this is this feature which can be moved in front of the sensor, and we can produce this kind of image. Another Oneshot test bench. The first one is 1.5 gigabit SerDes, and we had two boards. One transmission, one reception. So we can irradiate one device while the other one is used to check the previous one and then change device. The main difficulty for this test was the data rate. We have to compute 300 megaoctets per second, and also you have to have in mind that you have many, due to the data rate, you have some bits which are stored in the connection, in the data path. It means that it's difficult to synchronize the two boards. The second test board was for the SCOG3. It's an ASIC which I think it means space computer on chip, and it embeds a lot of things like Leon 3, 1553 interface, and so it's a lot of things, and it means that we have to develop a lot of elementary tests to cover all the functional units which are embedded in this device. And for this kind of test, the main point is you have a high workload for test development. And when I say high workload, I'm talking about many hundreds of hours. Now, Mirko.
Okay, thanks, Christian. So, one special test setup we have at TESAT, we are using at TESAT, is the RFSE testing setup. So, up to now we have tested moderate power devices up to around 10 watt RF power. That was no problem to perform these tests at UCL, but here we had to test RF power devices above 80 watt, and so it was not possible to test this in vacuum. So we decided to go to an in-air facility, and we decided here at the KVI. They are providing an in-air beamline with a 29 MeV per nucleon, and so it's possible to perform this test there in air. So, the test setups quite complex, especially because of high RF power. The RF power handling capability, I need a rotating Peltier cooling unit, and all these has to be driven in and remote in this facility. Okay, the challenges in the preparation phase was the KVI is not fully established by ESA and all the other. They are in the starting phase for the space testing, and so a lot of simulation have to be done before we start with the campaign. We have the initial energy and make the degradation of the ion to have worst case conditions. So yeah. Then okay, we have to adapt the setup for this facility. As I said before, we have performed the former test at the UCL, where we can go directly to the vacuum chamber and connect it. And here we have to do it in a remote with a similar setup. So then, okay, we have to procure in the preparation phase all the RF equipment for this special frequency which we use here, and also for the high power handling. Then, okay, as I said, the KVI, we have to do some things, not only the beam simulation, also that they provide the correct field homogeneity. We need to know the flux and fluence and so on. So things that had to set up in the KVI. So then afterwards, it was better for us to validate again the beam quality by using reference devices. And okay, that's all. Also you need to react if something happens what you not expected. You have to change the whole thing story and have to look what's going on. So and of course the more complex this test system, you might extra time need for setup problems. Yes, and for sure, yeah, we can also record the transients we observed during the RFSE test campaign, and yeah, it's a lot of test data accumulated during the test campaign, and it has to be analyzed and put into a report. Best would be managing one slide where all the information is included and everybody can see that.
Thank you.
Okay.
So, okay, so now we are talking quickly because the chairman requested me to speed up. The best setup for me, it's able to operate the device in a real condition. I mean, in a condition it will be used on flight. And the main point is it has to be able to detect and record any abnormal behavior induced by heavy ion. But sometimes it's difficult because triggering a complex signal is not so easy. Also, I think it's useful to be able to monitor online all DC parameters because it can give additional information. It can be also possible to change easily and fastly to reconfigure the test condition. Mainly because sometimes you have to check for different application condition of a device, or sometimes also because what you're expecting before the test is not the reality, and you have to adapt the test setup. It has to be remotely operated. Sometimes the distance is very close, like in UCL, but sometimes it can be up to 80 meters, and maybe more. It has to withstand vacuum condition, and a lot of things I forgot. And the last one is fits in a small suitcase so as you can bring it with you directly to the facility and not too heavy. But the facility, I think a lot of people here know what are the different facilities. Main thing is that in Belgium and Finland, in Belgium mainly we can only irradiate under vacuum, and in Finland we can select vacuum or free air, and all facilities only offer free air irradiation. The last point I just want to talk about is device preparation. More, as you know, if we, in the real life, the cover does not protect the device, but when you are going to an accelerator, we have to remove the layer on top of the die to expose it to the beam. And more and more, we have to test plastic devices. And plastic devices opening is not always easy. And we have now different tools like laser opening machine and as well as chemistry, which give us capability to open device. And we succeed also to open in a good condition copper bonding device. In conclusion, we have many testers available. We have the capability to carry out tests in a rather short delay, a few weeks, at a cost which is always too much for the project manager, but it's not my point of view. We also have the capability to develop on demand test setup for a complex device. We have in-house also a team of designers we can ask. We have access to many facilities, and now I think our experience is enough to select which one is more suitable for a test. We also have in-house device opening capability, which are now very efficient for plastic packages. And the last point is for testing, this is a general sentence, good electronic skills are requested for test setup development, and also recommend to have a good knowledge of the device you test, otherwise you may miss different things. So it's finished, but come to me after the presentation. Thank you.